In this video, I will talk about C, the semiparametric estimation methods for VAR. Right, I will talk about two different methods. The first method is referred to as the GEV method. You probably recall the GEV distribution, which arose from definition 1 of extreme values. So suppose the data follow definition 1. Of extreme values. Now, just to refresh your memory, this is the picture I showed you a long time ago. So under definition 1 of extreme values, you pick the extreme value as the largest data point over a long period of time, in this case 1 year, right? So this is the only extreme value, okay? And this is definition 1. You probably recall this. We did this some time ago, right? And under this method, the CDF of the data of the extreme value can be approximated by the GEV distribution. You probably recall this. Now, in order to find the value at risk, we need to set the CDF equal to P and solve for X in terms of P. So that's what I'm going to do now. Right. Now, if you solve this for X in terms of P, this is what you will get. I'm sure you guys know how to do it better than me. So this is what you will get as a solution for X in terms of P. So hence, the expression for VAR is equal to this. Okay. Now there are three parameters: mu, sigma, and psi. Now what I'm going to do is I'm going to estimate some of these parameters non-parametrically and the remaining parameters parametrically. So I will estimate the psi parameter, which you may recall is the shape parameter, as follows. Right, where k is a number between 1 and n, and the data are arranged in a descending order or decreasing So this is the largest loss, this is the second largest loss, and so on until this is the smallest of the losses. Right. Now this estimator given by this equation, if I may put it in a box, right? This estimator is known as the Hill's estimator, Hill, and this is a non-parametric estimator. The reason being, if you look at the right-hand side, right, it only involves data, right? These are just data arranged in decreasing order, and k is a fixed number between 1 and n. So what I'm saying is that this is a non-parametric estimator. Right? Okay, and so that's part one. Part two, there are two other parameters that we need to estimate, okay? And these are the mu hat and the sigma hat. So I'm going to take mu hat and sigma hat as the MLEs of mu and sigma respectively. Right? So remember, the method of maximum likelihood estimation assumes that the data comes from a specific distribution. Hence, by definition, that these two estimators must be parametric. Must be parametric estimators. Because, as I just said, the method of maximum likelihood, to apply the method of maximum likelihood estimation, you must assume that the data comes from a specific distribution. Right? Hence, the estimator for var, right, given by this equation here, mu replaced by mu hat, sigma replaced by sigma hat, psi replaced by psi hat, this estimator is an example of a semiparametric, is a semiparametric estimate of var. The reason being that psi hat is a non-parametric estimator, but mu hat and sigma hat are parametric estimators. So you're combining parametric and non-parametric estimators. Hence, what you have here is a semi-parametric estimator for var. All right, so that's the first method I wanted to talk about. The second method, for the second semi-parametric method for estimating var is known as the GP method. GP in this case stands for generalized Pareto, which you must recall. Suppose the data follow definition 2. Definition 2 of extreme values. And you probably remember definition 2 of extreme values. This is, I will just show you the picture just one more time in case you forgot. So this is definition 2. Definition 2 of extreme values. So this is where that anything, any data point that exceeds the threshold denoted by U is considered an extreme value. So in this case you have 11 extreme values, right? And under this definition, the CDF of the extreme values is given by this distribution. You must recall this from what we did earlier. This is the CDF of the generalized Pareto, or the GP distribution, right? Where for x greater than U, where Q denotes the probability that x is greater than U. So you may recall that this is the GP distribution, the CDF of it. Now to find the value at risk corresponding to this, I'm going to set the CDF equal to P, right? Which implies that 1 minus is equal to P. And if you solve this for x in terms of P, this is what you will get. All right, so hence the value at risk, right, is given by U plus sigma by psi okay. Now there are two parameters in this expression, sigma and psi. Now I'm going to estimate them differently. So I'm going to estimate psi as by the Hills estimator, which I mentioned in my previous slide. Okay, so this is, I will write it one more time anyway. So this is the Hills estimator I mentioned just a few minutes ago. So k is a number between 1 and n, and the data arranged in a decreasing order. All right. Okay, so this is let me once again put this in a box. And this is once again known as the Hills estimator. All right, so by definition, this is a non-parametric estimator. Now, part 2, I'm going to estimate sigma hat as the MLE, which by definition assumes that the distribution, the data comes from a distribution, hence sigma hat must be a parametric estimator, right? Okay, so the psi hat is a non-parametric estimator and sigma hat is a parametric estimator. Hence, Hence, the following estimator for var, right, u plus sigma hat the following estimator is a semiparametric estimator or estimate of var. Alright, so this completes the second method. Right, and this also completes the semiparametric estimation of var. In the next videos, I will talk about estimation of ES, the second risk measure, because so far we only talked about estimation of var. Alright, so in the next 3 videos I will talk about how to estimate expected shortfall. Right, parametrically, non-parametrically, and semi-parametrically.